The ArcelorMittal BD Eastern Service Workshop is where some of Europe's most critical railway components are born. This facility produces solid wheels, tired wheels, and axles for trains and trams, all manufactured to exacting EN, UIC, and CSN international standards, the same specifications that keep millions of passengers safe every day. The heart of the process is heat treatment, performed in both gas-fired and electric furnaces. Each furnace is lined with refractory brickwork or high-temperature ceramic fiber insulation to hold precise temperature profiles. Every cycle, from heating rates to soak times to cooling curves, is computer-controlled and continuously logged by a dedicated heat treatment data recording system. That digital audit trail isn't just good practice, it's a regulatory requirement for safety-critical railway components.
Now, here's something you might not expect to find fascinating. Chains. Not just any chains, though. We're talking about Campbell Chain, one of America's most trusted names in heavy-duty chain manufacturing, a company that has been forging strength into steel for well over a century. So how does a chain actually get made? It all starts with step 1, wire drawing. Long steel rod is pulled, literally drawn, through a series of progressively smaller dies, stretching and tightening the metal until it reaches the exact diameter needed for each chain size. This process also work hardens the wire, giving it the toughness it needs before it's even shaped. Step 2 is forming. Automated machinery bends each length of wire into an oval link shape with incredible precision, thousands of times per minute. Then comes step 3, welding. Each link is flash welded shut using a precisely controlled electrical current. The heat fuses the steel at the joint so perfectly that the weld becomes the strongest point on the entire link. Not the weakest, the strongest. Step 4 is heat treatment. The chains travel through a specialized furnace where they're brought to exact temperatures and then quenched and tempered. This process transforms the microstructure of the steel, delivering that perfect balance of hardness and ductility. Finally, step 5, quality inspection. Every chain is proof tested under load, and inspectors check dimensions, surface quality, and performance. This is the Acme APK 1000 profile bending machine, and it is an absolute workhorse. Built in Turkey by Acme, one of the world's leading heavy machinery manufacturers, the APK 1000 is engineered for one specific purpose: bending heavy structural steel profiles with controlled, repeatable precision. We're talking about the kind of machine you'll find in shipyards, bridge fabrication shops, steel construction companies, and industrial facilities around the globe. So what makes it special? It's all in the rolls, or as engineers call them, the rollers, or rouleaus. The APK 1000 uses 3 precisely positioned rolls to apply gradual, even pressure across the full length of a steel profile. Unlike press brakes that make sharp bends, this machine curves the metal smoothly, following a radius that can be dialed in with remarkable accuracy. And what can it handle? Just about everything in the structural steel family. I-beams and H-beams, those heavy flanged sections you see in building frames. U-channels and C-channels used in support structures. Angle iron, the L-shaped sections found in everything from staircases to machinery frames. Round pipes and tubes, which need to be curved without kinking. Square and rectangular hollow sections. And solid steel bar stock for specialized heavy fabrication. The APK 1000 can handle profiles up to 1,000 millimeters in section height, hence the name. And it delivers bend radii with the kind of consistency that manual bending could never achieve. It's powered by a heavy-duty hydraulic system with rolls driven by a robust electric motor setup, giving the operator full control over speed and pressure. Deep in the mountains of Colombia, in small workshops that haven't changed much in 100 years, craftsmen are making one of the most essential tools in the rural Americas, the machete. Let's walk through it together. It starts with raw steel, typically high-carbon spring steel, often salvaged from old truck leaf springs. The steel is cut into rough blanks, sized for the type of machete being made. Next comes the forge. The blank is heated in a coal or wood-fired forge until it glows a bright orange yellow, somewhere around 1800 to 2000 degrees Fahrenheit. The smith reads the color of the steel like a language, adjusting the heat by sight and experience. Too cool, and the steel won't move. Too hot, and you'll burn it. Then the hammering begins. Using a combination of hand hammers and power hammers, the smith draws out the blade, spreading and thinning the steel from the spine toward the cutting edge. This process, called drawing out, takes multiple heats. The blade is shaped, the bevel is established, and the taper toward the tip is carefully controlled. Once the rough shape is achieved, the blade goes to the grinder, a large abrasive wheel that refines the bevel, thins the edge, and removes the scale left by forging. Skilled grinders work by feel and sound as much as by sight, knowing when the edge is right by the way the wheel bites into the steel. Then comes the critical step, heat treatment. The blade is heated once more to its hardening temperature, then quenched, plunged rapidly into water or oil. This sudden cooling locks the carbon in place, creating a hard martensitic steel structure. But hardened steel alone is brittle, so the blade is immediately tempered, reheated to a lower temperature around 375 to 450 degrees Fahrenheit to reduce brittleness while preserving hardness. Finally, the handle. Traditional handles are carved from hardwood, often local species like guayacán or nogal, shaped by hand and fitted to the tang. Some makers wrap the handle in leather or use synthetic materials, but in the oldest workshops, solid wood is still king. The finished blade is hand-sharpened on a stone wheel, polished and inspected. This is Pokom Milling Technology, a German precision machining company that has built its reputation on pushing the absolute limits of what CNC milling can achieve. And today, they're tackling something that looks simple but is anything but a pointed cone hat. Total weight, 1.5 kilograms of solid steel. Now, you might wonder, why is a cone hat impressive? Because of what's on the surface. The entire exterior is covered in an intricate, overlapping scale pattern, dozens of precisely shaped three-dimensional recesses machined into a curved compound surface. The machine used here is a 5-axis machining center, meaning the cutting tool can approach the workpiece from virtually any angle simultaneously, rotating and tilting in real time as the spindle moves through its toolpath. The process begins with roughing, removing bulk material quickly using large end mills to establish the basic cone shape. Even this stage requires careful toolpath planning to avoid vibration, chatter, and tool deflection on a conical workpiece. Then comes semi-finishing, a pass that brings the surface close to final dimensions, leaving only a thin layer of material for the final operation. Finally, finishing passes. Using small diameter ball nose end mills, sometimes as small as 1 to 2 millimeters in diameter, the machine traces the complex scale geometry across the cone's surface. The step over, the distance between each pass of the cutter, is measured in fractions of a millimeter to achieve the mirror-smooth surface finish you see in the final result. This is the Reed Model 740, a large-capacity thread rolling machine built for serious heavy-duty work. Today, it's rolling a single-start Acme thread, 4.5 inches in diameter, 1.5 TPI. That's 1.5 threads per inch on 1045 CDS steel. Let's break that down. 1045 steel is a medium carbon steel known for its excellent strength and machinability. CDS stands for cold drawn seamless, meaning this bar stock was drawn through dies at room temperature, which compresses and aligns the grain structure of the metal, resulting in tighter tolerances and better surface finish than hot-rolled steel. The Acme thread form itself has a 29-degree thread angle, that wide, trapezoidal profile you see on lead screws, vices, and heavy power transmission applications. It's been a standard in American industry since the late 1800s, designed specifically to handle both the axial forces and the side loads that come with power transmission. Now, thread rolling versus thread cutting. This is important. When you cut a thread with a die or on a lathe, you're removing material. When you roll a thread, you're displacing material. 2 or 3 hardened steel dies are pressed against the rotating workpiece with tremendous force. On a machine this size, tens of thousands of pounds, and the steel flows plastically outward, forming the thread without removing a single chip. The result? Thread rolling produces a stronger thread than cutting. The grain flow of the steel follows the thread form rather than being cut across, which increases fatigue strength by 50 to 75% over cut threads. The surface finish is also superior, often reaching 32 micro-inch RA or better without any secondary operations.